Hi everyone, welcome to our new One Word ABC seminar. It's my pleasure having here Josh Bond, who relatively recently joined um, Paris University, in particular Paris Dauphine, and he will talk about Bayesian score calibration for approximate models. Thanks a lot, Josh.
Thank you. Thank you for the introduction and for the invitation. Very nice to be talking here in one world virtually. So today I'll be talking about this scoring rule calibration, score calibration work that I've been doing for a little while now. So I'll go over some motivations and intuitions over what the method is. I'll go through some theory and explain exactly how the method works. I'll give some examples and just want to point out that this is joint work with Christopher Dravandi at QUT, David Warren at QUT, and David Knott at NUS. So very much a teamwork of the team here. So the main motivation for this work pulled from looking at how to estimate Bayesian models or draw samples from Bayesian posteriors where the likelihood is intractable. And so these little rascal likelihoods are basically very hard to pin down because you can't write out what the likelihood is and you can't evaluate the likelihood point-wise. So when you get data that is generated from this process that should have this likelihood, you can't go through Bayesian inference in this or sampling from Bayesian posteriors in the standard way. And typically current methods to do this, such as approximate Bayesian computing and pseudo-marginal MCMC, take tens of thousands of realizations of the data generating process, which, if that's the main computational cost that has a significant computational cost to draw realizations from the data generating process, then you can imagine that it's going to really slow down doing inference for these, or doing Bayesian inference for these types of models. And also, when you use methods like ABC, you may not be targeting the true posterior. So you're not really sure about how well you're doing and in terms of targeting something that makes sense for your problem. And it's also unclear how to identify when the method works, or more importantly, when the method has definitely failed. But in these situations, we do have lots of approximations at hand. So we have likelihood approximations. There's a host of literature, frequentist literature on how to approximate likelihoods from limiting distributions, which can be helpful if your process has a likelihood that is intractable to default to what the likelihood for the limiting distribution should be. Things like the Whittle likelihood. You can use some kind of model simplification, so you can go from an SDE to an ODE, or you can also use something a little more sophisticated like a linear noise approximation. So there's lots of likelihood approximations that are available to use. There's also posterior approximations, so you could use a Laplace approximation or INLA. You could use variational inference. You can use approximate Bayesian computing. And there's also sampling approximations, so importance sampling, SMC, MCMC, and the posterior approximations and sampling approximations don't really help with the intractable likelihood scenario. But you can imagine that if you have a intractable likelihood and you make a likelihood approximation, you're also going to have approximations to do with the posterior, or from taking samples from this approximate posterior. So essentially, all along your pipeline is approximations. So we have these approximations, and we can learn functions. So to expand upon that, if I have approximated a posterior with Monte Carlo samples, so meaning I have an approximate likelihood, and I've taken I've defined an approximate posterior with that approximate likelihood, and I have Monte Carlo samples from that approximate posterior, then I could find a function, I could learn a function to correct the approximate samples of the posterior, and with no need to rerun the MCMC. So I would take the output of, say, the MCMC, and I would try and transform those samples such that they're closer to something that's better or known. In our case, it would be the true posterior. So, sorry, my dot points have kind of messed up a little bit here, but if you were to correct the approximate likelihood directly, you would have to rerun the MCMC every time. So the idea here is if we act directly on the approximate samples from the approximate posterior, which is defined by the approximate likelihood, you only have to run the MCMC for that set of data once. And our method, we're going to use simulated data as well. So we do have to run MCMC for approximate posteriors on that simulated data, but you can do that in parallel for multiple data sets. So here I'm being a bit vague with what the method is, but I'm just saying our motivation for taking the output, which is approximate samples from MCMC from using an approximate posterior, which uses an approximate likelihood, is that we only have to do the MCMC once. We don't have to go back and rerun the MCMC with a likelihood that's been corrected. So a little illustration kind of help us to get where the motivation is coming from. If I have from left to right a prior, I generate a point in red from that prior. Somehow it's gotten right in the middle. I didn't do that on purpose. And then from that point, I draw data from the data generating process. And then I use an approximate posterior, so this is in blue, to kind of construct the posterior that I would like to get. And then in purple, it shows what the true posterior should be. And so here, the approximate posterior is biased. It has the right uncertainty quantification, but it's biased. So here, what I would like to do is I would like to find a function that transforms the blue in the posterior facet into the purple. Some function that essentially corrects the bias. But of course, I don't actually have the true posterior, so I can't compare those two things directly. So finding the function to do that, that bias correction, or it can be more sophisticated, but essentially for this example, the bias correction, I can't do it directly. So the idea comes from if I do this many times, so for each row here, I drew a point from the prior, I generated data from the data generating process, and then I constructed the approximate posterior. If I do that many times, I can see how close my approximate posterior gets to the value that generated the data. So it's this kind of like calibration idea. And if I were to do a correction, I can learn how to correct on average over all of those posteriors. So to do that, I would need to somehow measure the similarity. So here I've got an illustration of what I was doing, and here I've got some mathematics around it. So I draw from pi, which is in purple my prior. I draw simulated data, that's what the tilde is for, from the data generating process P. And then I want to somehow compare the approximate posterior, which is K, with the point that generated the data. So this is what this S is, this comparison that's comparing the similarity between the point that generated the data and the approximate posterior that I ended up getting. And the expectation here would be over all pairs of theta and the simulated data. So that's what this averaging across the rows would be. So if I were to look at some kind of similarity measure, what I could do is I could say, well, I'm going to use this transformation idea. So I use a push forward on the approximate posterior. And that way I don't need to run MCMC again if I have samples from K that are based on an approximate likelihood. I just do it once, and then every time I want to try a new function to transform these, I would just apply that function. And then I'd want to find the best function to use in a class of functions, script f. So f transforms realizations of K. So here it could be a bias correction that pushes all of the approximate posteriors in the correct direction of their theta, which the simulated data they're based off was generated from. So what would that do? Before correction, we have all these posteriors being slightly off, and then after correction, it would move them all to be much closer. So on average, we're doing better. If it was just a bias correction. So this is where this idea of model calibration by simulation comes in. So we have all these pairs of true parameters for your process, simulated data from that, given that true parameter that comes from the true data generating process, and then an approximate posterior, which we know is wrong, but we'll use those pairs of the prior and predictive, the values of the parameter and the simulated data to correct the posterior. So if I wanted to get correct coverage, I could choose something like this, where I take the approximate posterior, I apply this function to it. So it's the push forward, and I compare the two by saying, well, the credible regions at the alpha level from the corrected approximate posterior or the adjusted approximate posterior should be approximately equal to alpha. Any deviation of the credible region at alpha level from alpha, I need to penalize. So I could do something like that, but our question was, can we correct the entire distribution? So can we be Bayesian about it? Can we recover what the true posterior was, at least in approximately or in some sense? And to do that, we use proper scoring rules. So we use these proper scoring rules. So that's kind of the motivation and the illustration of what's happening. Let's talk about what theory and backs it up and what the method actually ends up looking like. And so if anyone wants to, maybe now's a good time to jump in if anyone wants to ask a question about what's been discussed so far. Okay, feel free to jump in. So scoring rules take in their first argument a distribution, and in their second argument a point. And so it's going to compare the probabilistic forecast U, which is a distribution, to a ground truth X. And if we can define the scoring rule between two distributions as just taking the expectation of the second argument with respect to V here. And proper scoring rules, or strictly proper scoring rules here, is the scoring rule is strictly proper if when I compare V to itself, it's greater than or equal to any other distribution U I could choose for all V in some family. And equality holds if and only if U is equal to V. And basically it means that if I try and use the scoring rule in a maximization problem, I'm able to recover that V is the best distribution where V is the best distribution, and I am able to recover it in the class of U. So to use scoring rules for our work, I guess, alluding back to the picture I first showed where I didn't have the true posterior, so I couldn't do that naive method. Ideally, I would like to find the push forward of the approximate posterior here in K, so F hash K, and then I would like to compare it directly to the true posterior, which I've written here as pi given Y. But I can't do that because I don't have the true posterior. So this is equivalent to saying, well, the scoring rule is just the expectation with respect to the true posterior. And then we do a little trick. So here we replace the expectation with respect to the true posterior with this idea that the joint posterior with the marginal data distribution is equal to the data generating process times the prior. And so that's the trick used in Pesciati and Data and also in our paper. And so basically, if we wrap this first maximization problem up and take it, the expectation with respect to the marginal data distribution, then we'll end up with this problem where we have the data generated from this marginal distribution, the theta generated from the posterior, and we can do a switch. So we can say that if we generate theta from the prior and we generate data from the data generating process and we use this scoring rule, we should recover the posterior under some assumptions, but we should recover the posterior. We should be doing an optimization that is targeting the true posterior without actually having to know what the true posterior is. And we can actually take this idea 2 steps further, and that's what we do in this paper. It's our main, I guess, methodological contribution, is that we replace we're allowed to replace the marginal data distribution with some kind of change of measure, where the change of measure is just here, this function v. And we can also replace the prior with some other distribution pi bar. And so long as we correct that replacement with an importance weight or with importance sampling idea, and it still works. So it's been a bit hand wavy so far, but let's talk about what the theory is here. So if we have a strictly proper scoring rule S with respect to cal P, script P, we have an importance distribution pi bar, and we will be able to calculate the importance weights to get back to the prior. And we have a stability function V, which controls this change of measure, and it's measurable. And a family of kernels K, which we're willing to optimize or try and find the best kernel in that family for. Then if that family of kernels is sufficiently rich, then I will recover the K star, and K star is the true posterior for all values of simulated data. And so the weights here just correct for the fact that I used pi bar instead of pi. And then I have this free stability function V that I can choose however I'd like. And so in this theorem, the condition here that K is sufficiently rich is doing a lot of heavy lifting. So there might have been a question.
Yeah. So there was a question from David. I don't know, David, feel free to unmute yourself if you want to.
Thanks. Josh, could you go back to the first definition of the problem, if you might mind? It's like 3 slides back. One more. So the one before that, with just before you do the expectation trick. Okay, right there. So yeah, so this is a score. So one forward. Sorry, my bad. So this is an expected score over parameters, right? There's nothing about this that's taking expectation over the data. So when you go to the next slide where you're taking the expectation over the data as well, this is now technically a different scoring rule because it's like the expectation of the expected score over the parameters. So the first thing is an expected score, and it's proper, right? I agree with that.
Yeah.
But when you start overlaying an expectation over top of that, it's no longer as an interpretation as an expected score, though. It's like the expectation of an expected score. You see what I'm saying? So I agree that,
I
like,
see what you're saying. Is the point like a terminology point, or you think there's a problem?
I don't know if there's a problem. So generally speaking, scoring rules are finicky objects.
Yeah.
And when you start playing around, when you do little weights and things on them, and when you start taking expectations of other things, they can be they can lose the interpretation they used to have. It's like a good example. This happens all the time in the literature on scoring rules, where you have things like inadmissibility and stuff because you have these little changes in the scoring rule, and they can lose propriety. And then, have you investigated any of this?
No, I'm not aware of that literature. I think we only use the fact that S is a proper scoring rule under the original expectation.
Okay.
We don't assume that it's a proper scoring rule under this
Data measure, I guess.
extra expectation. So it's for every y tilde according to the marginal data distribution that we need S to be a proper scoring rule.
Okay. I'll have to think about that. Thanks. I just was wanting to clarify. Thanks, Josh.
Yeah, I mean, I'll go back and look at the proof with that angle and see if it makes any difference. But yeah, when I was going through it, it was definitely it was not relying on the entire expectation, or not relying on S to be proper under both expectations, but just under the first one.
Okay, cool. Thanks.
Yeah. But I'm very happy for you to point that out, because that means I can go think about it some more. Yes, and check my my theorem. So here I was saying that this condition that script K is sufficiently rich is doing a lot of heavy lifting. So we need, what does sufficiently rich mean here? So if we have K to be a family of Markov kernels, P to be this class of probability measures, Q to be a probability measure on the data, and pi given y tilde to be the true posterior at y tilde, then we say that K is sufficiently rich with respect to Q and P if for all the U in K, we have that the distribution or the probability measure that you get by conditioning on y tilde belongs to P almost surely, and there exists a U in this family of Markov kernels such that you can recover the posterior for any data set y tilde. So that is a very strong condition, and that's one of the I guess the drawbacks of this theorem. But later on, I'll talk about why it's okay to make, or why in practice it's okay to make that assumption, because we have some ideas of, in the paper and in my appendix of these slides, which I can talk about if we have time, we have some ideas that for the class of kernels that we consider and the way that we choose our pi bar, so our importance distribution, we have this notion of asymptotically sufficiently rich. So with enough data, the amount of correction that you need to do gets less and less. And I'll just double back for a second and point out here I was very generic and said that script K is this family of Markov kernels. We're just going to consider the family of Markov kernels defined by the push forward on the approximate posterior for any data set given any data set that constructs that approximate posterior. But you could use this theorem for any class of any family of kernels, meaning that you could do optimization directly over the space of kernels or some family of kernels other than the push forwards that we're going to use. Okay, so an overview of Bayesian score calibration. We generate samples from this importance distribution. Then we generate data sets from the data generating process, given the value drawn from that importance distribution. And then we calculate approximate samples from our approximate posterior. We plug all this into the optimization problem, where we do essentially like a Monte Carlo approximation to that expectation. And we find the best function that pushes the approximate posterior towards the value that the data was generated from. And in the end, we can apply that function onto the approximate posterior for the actual data. And then at the end, we can calculate some calibration diagnostics from the fact that in the end, we only wanted to correct the approximate posterior for one data set, but in order to get to that point, we ended up correcting the approximate posteriors on average for many data sets. And from that extra information, we can kind of see like how well did our function learn the correction on average. So there's, for free, essentially, from the method, there's some additional like diagnostic data to see how well has the method done, has it failed, has it done well enough for us to use it. And I'll show some examples of that in the next section. So for the moment, we have been focusing on this moment correcting transformation, where essentially we correct the bias with just a linear correction, and then we correct the variance with this L. So if we take the mean to be the approximated mean from the samples from the approximate posteriors, then we can basically do this bias variance correction of this form. And well, if you go back to here, you can see that this weight function behaves all well and good in theory, but if you're doing a Monte Carlo approximation of that expectation there, then you have to be careful about the variance of the weights. And funnily enough, we were very brave and did something that I would have thought was quite dumb. But sometimes when you're brave, you don't end up like this. You actually end up with something that works well. And so we started investigating what happened if we just ignored the weights. How well did the method do if we completely ignored the adjustment that we needed to do to guarantee theoretically that we're targeting the true posterior? We just ignored that and we set the weights to 1. And it worked empirically so well that we had to figure out why. And what we have realized is that because of the extra flexibility in the problem with this v function that you can choose to be rather arbitrarily that you can choose, if you select it to be something very particular, then asymptotically, the weight function will tend towards 1 anyway. So there's a justification for v being, well, there's an asymptotic justification that you can set the weights to 1. So now for some examples. The first example I'll do is for a OU process. We just have 100 observations for the final time t, and this is what the likelihood for that final time t should be, where we fix some constants, and we're gonna, instead of using that correct likelihood, we're gonna use this approximate likelihood, which is based on the limiting distribution of the process x. And when we do that and we apply the method, the approximate posterior for the 2 parameters, so we've got mu and d here, is in blue. And when I use the correct weights, so that's with in green with the 0 there, I get I get 2 posteriors that look kind of good compared to the true value, which is this x. And then if I use the unit weights, I actually get, for mu at least, I get a posterior that's even closer to the true posterior than I would have if I had have used the correct weights. And so what's going on here is there's a trade-off between when you set the weights to 1, you get to use all of the samples to learn what f should be. And when you leave the weights to vary as they should, then your effective sample size for the Monte Carlo approximation of the expectation essentially goes down. So you can't learn as well what the f is. So for for data sets that are large, the unit weights would be okay, but for data sets that are small, we would say that it's not going to be okay. And here we've used the importance distribution to draw what the true parameters should be. We've taken our original approximate posterior for the true data, and we've scaled it by 2. And that's just so that we have, well, it's basically to safeguard against, if we're going to choose to use the approximate posterior, we want to be sure that the approximate posterior covers what the true value should be. So that's why we've scaled it by 2. And just some numerical results from this example. So alpha equals 0 is using the correct weights, alpha equals 1 is using the unit weights. And so basically the unit weights and the correct weights do much better than the approximate posterior, and the unit weights get much closer to what the true value should be. So that was for mu. And for D, it doesn't change all that much because D was already doing quite well. But here, actually, the adjusted posterior for the correct weights had worse coverage than the approximate posterior. Okay, so the next example I want to go through is this Lotka-Volterra SDE. And this example comes from a Turing JL tutorial. And I've asked this question at the past few times that I've given this talk. But in this tutorial, they have, it's here in the Turing documentation, they have this idea that they say we use a quasi-likelihood approach. And I don't know what that means, and there's no reference. So basically, they are going to do an ABC style approximation to this SDE problem. But instead of fixing their tolerance. So, sorry, a noisy ABC style approximation. Instead of fixing their tolerance, they're going to let their tolerance be another unknown parameter in their inference. So if anyone has a reference to some people in the literature who have done this, I'd really like to know about it. But so far, this is just, I saw it in the tutorial. I didn't think it would work. It kind of worked and also kind of didn't. And I was wondering whether we could correct it with our method. So there's no guarantees asymptotically or otherwise that I know of for using this style of approximation. Okay, so essentially it boils down to being a noisy ABC style likelihood. And on top of that, we're going to do a further approximation where instead of using a very tight numerical integration scheme, type being small, very small, or even like automated choice of time steps, I'm just going to set the difference in the time to be 0.01 and use a EM style approximation of the data that I simulate in order to construct this quasi likelihood. So basically does this. So my adjusted posterior, this is with unit weights, is in orange here. And the approximate posterior is in blue. So for each of these parameters, I would argue that it does better. For beta 2, it does a lot better. For beta 4, it kind of expands the variance. So maybe you could argue that's not better there. But from this plot, it's not clear, except for beta 2, it's not clear whether the adjusted posterior or the approximate posterior does better. And that's where this calibration diagnostic comes in. So we can take all those pairs of true values and then adjusted posteriors that we've learnt the adjustment for. We can take all of those and we can construct many different types of diagnostics, but here's the one that we've been using the most. And it's a target coverage versus the coverage that we get from the adjusted and approximate posteriors. So on the right-hand side, just using the approximate posterior, the marginal coverage for beta 1 through beta 4 is very poor. So it's well below what it should be nominally. But when we use the adjusted posterior, it does a lot better. And if this were, if you looked at this coverage plot and you said, okay, for the adjusted posterior, for beta 1 through 3, it looks like it's a little lower than we would like it's outside of this 10% band, but it's okay for our situation, then you would go forward with this correction and with this model. But if that still wasn't good enough, you would likely conclude that the combination of the approximate posterior that you chose and the transformation that you're using to correct it is not sufficiently rich. Like it's too far away from being sufficiently rich to be useful for your purposes. So you would either want to try a more general transformation to see if you can get better corrections from your approximate posterior, or you would want to try a different approximate posterior to then correct. So I have done some recent work to look at another type of approximate posterior for this problem. So instead of using the quasi likelihood, which I don't know where it comes from or why it's justified, I used extended Kalman filter. So use this Kalman filter as an approximate likelihood. What does that do? You discretize the SDE at time points t0 through to tn. You assume that it's Gaussian at each ti, and you do the update for each Gaussian distribution by the dynamics that are implied by the SDE, but with this linear assumption. So essentially, you know that every time You start at a Gaussian distribution, you're going to transform to another Gaussian distribution. So if you choose to use the EKF as what approximates your likelihood, then you get this type of calibration diagnostic where you can see that the coverage is quite low still for the approximate posterior, but the approximation is able to learn with just this bias and variance correction, a corrected posterior, which on average across these simulated data sets has much better coverage properties for all of the parameters, not just beta 4. So thanks for listening. This is ongoing work still. I'm happy to talk. Thanks to Chris and David Squared. Also, thanks to Ming and Ard Vandervaart for having helpful comments last year that helped improve the paper. And if you want to get in contact, there's my email, and I'm on Twitter, but probably better to email these days. And some references. And if there are any questions about the unit weights or the asymptotically sufficiently rich, I have some slides hidden at the back of this slide deck. So let me know what you want to talk about.